Alright, so this video is going to be on angular momentum. This is picking up on page 14 in your momentum packet, section 11.6. Yes, I am aware I'm skipping around. I am trying to cover the most important parts first. If I seem particularly awkward in this video, that's because I'm trying to record with poor Miss Brand in the room, who's having to listen to me talk to myself. So that's, me being even weirder than normal. But on the bright side, I seem to have figured this whole recording myself with my phone thing figured out. It's hilarious that my phone is a way better document camera than my document camera. But now we know. Alright, so section 11.6. Consider the point mass m moving in the circle below with the velocity v and a radius r. This particle would have a linear momentum p. Remember that letters concerning momentum make no sense, that equals, hopefully you remember this since we literally just did this unit, but linear momentum is going to be mass times velocity, so mv. But it also has an angular momentum because it's moving in a circle. Angular momentum is represented by an uppercase L. Again, there's no logic there, stop looking for it. And there is some logic here. Remember that the equivalent of mass for rotation is rotational inertia, which is uppercase I, and the rotational equivalent of velocity is angular velocity, which is omega. So this should look pretty familiar. It's basically the same formula, but in terms now of rotational quantities. Also, you'll notice a bunch in this section that I didn't know how to format things, apparently, and there's like awkward line segments. Just ignore them. The SI unit for angular momentum is the same as the SI unit for linear momentum, which is kilograms meters squared per second. Although I'm doubting myself a little, so hold on. Okay, I was right about these units. I shouldn't have doubted myself. Also, things just keep getting higher and higher stakes in here, because now Mr. Shillito and Miss Brand are listening to me awkwardly talk to myself, and potentially contributing.
Spinny things!
I was warned that was going to happen. Alright, so these are the same units you'll notice for linear momentum. I also seriously doubt the AP is going to be like, hey, what are the units for angular momentum? But there they are. So this generic expression for angular momentum, I omega, holds true regardless of the shape of the rotating object, which is important because we just in the whole last video on torque made a really big deal out of the fact that I, rotational inertia, is very dependent on shape. So that's already been taken into account here. So L equals I omega doesn't change, but the I will. That's kind of what this next question is saying. It says in the space below, write, start with the generic expression for angular momentum and derive the expression for angular momentum for a point mass, like the one in this picture. So we would say L equals I omega. Then for a point mass, you'll remember that the moment of inertia, or the angular, the rotational inertia, is mr squared. So angular momentum becomes mr squared omega. This, however, can be simplified even further because omega has a relationship with linear velocity that looks like this. Omega equals v divided by r. So then you have mr squared times v over r. One of the r's cancels, and you end up with mvr. Now this is an equation that's not on the AP formula sheet, L equals mvr, even though it is often used. It's the angular acceleration of a point mass. But it's not on the formula sheet because it's not really its own formula. Like so many other things we've talked about, it's a version of this, and the AP is like, we gave you L equals I omega, that's good enough. Let's work a problem using this. So a 2 kilogram grinding wheel with a radius of 0.1 meters has an angular momentum of 2 kilogram meters squared per second. If the wheel can be considered a uniform disk, what is its rotational speed? So as always, we look at what we've been given. We've been given mass of 2 kilograms, a radius of 0.1 meters, and an angular momentum of 2 kilogram meters squared per second. That's such awkward units. It says that we can consider the wheel a uniform disk, which means we know something about its moment of inertia. It's 1/2 mr squared. And what is its rotational speed? So if L equals I omega, and we plug in L equals 1/2 mr squared omega, then we can just plug in numbers. We get 2 equals 1/2 times 2 times 0.1 squared omega. 1/2 times 2, those just go away. 0.1 squared is 0.01, so then we have 2 divided by 0.01, and we end up with omega equals 200 rads per second. Alright, so if you move on to page 15, this is a direct continuation of what we were just looking at. It says, while the expression above for angular momentum for a point mass was derived for a point mass moving in a circle of radius r, so the equation it's talking about is L equals mvr. It can be applied to any object if r is defined to be the moment or lever arm. I've never really heard the term moment used in this context. Lever arm I specifically mentioned in my video on torque is often used instead of radius because it's not always obvious that it's a radius. It's the distance to the point of rotation, and that's sort of the same deal here. You will recall that the moment or lever arm is defined to be the, well, we don't remember that, we did not define it, but thanks reading guide, to be the perpendicular. I cannot spell perpendicular and talk at the same time. The perpendicular distance from the axis to the line of force, or in this case, motion. So it has to be perpendicular. So I'm actually in some of my problems going to write it as MVR perpendicular so that we keep that in mind. It's going to make things easier actually, although right now you're like, no, Ms. Schneider, what? So our textbook apparently gives the formula L equals RMV sine theta for angular momentum of a point mass. This relationship is valid, but it's easier to just remember MVR, where R is the perpendicular distance. This is the same thing as when we were dealing with work, and work was equal to force times distance times cosine theta, and it was annoying to have to remember to include that cosine theta, because in that case we always wanted to be dealing with the parallel component of the force. Here we want the perpendicular, so we would have to include sine, but if we just always only think about it in terms of perpendicular component, we don't have to bother remembering to stick that trig function on the end. And it actually makes problems like this next one a lot easier, because this says a particle can have an angular momentum around an arbitrary point in space, even if it's not actually rotating. Calculate the angular momentum of a 3 kilogram point mass about the origin of the system below when it is at position A and at position B, and it's moving linearly at 2 meters per second. So when I saw this problem and the associated diagram when I was working these out ahead of time, I was like, that looks awful. There's like 12 numbers and there's lines and my students are going to hate me. But the whole two things that we just wrote make this super simple, because I was like, okay, well, we're going to have to figure out how far it is from the origin at point A and point B, although it actually, the diagram gives you that, but I thought we were going to have to use them. We don't, because all we care about is the perpendicular component of the distance from the axis, which is this right here. This is our perpendicular. It's 2 meters. It's 2 meters the whole time. It doesn't change. So the angular momentum at point A is equal to the angular momentum at point B, and it's just mv r perpendicular. In this case, we have a 3 kilogram mass traveling at 2 meters per second with a perpendicular radius of 2, so we get that we have 12 kilogram meters squared per second. Neat. Alright, this whole next part is on the right-hand rule. If you'll remember, we went over the right-hand rule. Alright, so I probably awkwardly stopped mid-sentence, and I have no idea what I was saying because I have to stop approximately every 15 minutes because of this free software I'm using. But what I was trying to tell you is that we're not worrying about the right-hand rule right now. We went over it in class a little bit. It's not technically on the AP. Is it nice for you to know how to use it? Yes. Is it something we should worry about right now? No. So we're skipping that entirely, which is like half of this page, so that's exciting, right? This last part says, in the space below, write a series of equations that show the rate of change of angular momentum, delta L over delta T, how the rate of change of angular momentum relates to the moment of inertia, the angular velocity, angular acceleration, and or the net torque, which is a hot mess of words, but it actually is pretty cool if you look at it. So what they're saying is we have L equals I omega. So let's talk about what change in L over change in T would be. Well, change in L over change in T would need to be change in I omega over change in T. The moment of inertia isn't going to change within a problem because it's related to mass and radius, which aren't really things that can change. So we can rewrite that as I delta omega over delta T. Delta omega over delta T should look familiar because that's angular acceleration alpha. So that becomes I alpha. I alpha should look familiar from my last video because that's torque. I can't draw tau right now. That's definitely tau. So the result of all of this is the change in angular momentum over time is equal to torque. And this is going to have a really cool and hopefully really familiar result. Swapping pieces of paper. Because we can actually rewrite that in a way that looks familiar. You might remember that change in linear momentum was equal to force times change in time equals m times change in velocity. That's literally what we just did. We just did that change in L is equal to torque times change in time is equal to I times change in omega. Nifty. So, a couple of consequences of this relationship. If no net torque is applied to a system, the angular momentum of the system should be constant. Same thing if no net force is applied to a system, the linear momentum should be constant. When a net torque is applied for a period of time, the angular momentum should change. these blanks are not nearly big enough for you to write in. This can be thought of as the impulse momentum theorem applied to a rotating system. Impulse momentum theorem, I'm not sure we ever actually used that term. That's just, oh, this is the worst arrow ever. That's just the fancy name for this equation, because this is impulse and this is momentum. And now we just have it in terms of, instead of force and linear momentum, we have it in terms of torque and angular momentum. And these blanks don't have anything that goes in them, confusingly enough. Alright, example problem 14. When the water is diverted onto the wheel at a grist mill in the picture to the right, the wheel reaches its operating speed of 25 rads per second in a time of 30 seconds. So change in omega, because we're going from 0 to 0.25, is 0.25 rads per second. And our change in time is 30 seconds. Notice that I made a point here to write, it would be really tempting to just write that as omega equals 0.25 radians. It's not what we care about in this case. We care about the change in omega. And they're only the same because we started from rest. If the moment of inertia of the wheel is 1200 kilogram meters squared, I equals 1200 kilogram meters squared, what is the average net torque provided by the water hitting the wheel? So we would just use this relationship we just wrote out. Torque times change in time equals I times change in omega. So our net torque times 30 seconds equals 1200 times 0.25. I'm always really proud of myself when I can do basic math in my head, which is embarrassing because I should be able to do more than basic math in my head. But 1/4 of 1200 is 300. 300 divided by 30 is 10. Look at that, you guys. And so the net torque on the system is 10 Newton meters, which is, again, from the last video, the units for torque. Now, conservation, angular momentum by itself, it's like, okay, that's a thing. Now we can relate change in omega to torque. That's nice, Ms. Schneider. Conservation of angular momentum is where things get interesting. Josh, you were actually trying to ask me about this a while back, and I had confused myself and was like, I know we're going to talk about this, just wait. So hopefully this will suddenly make some things make sense to you. The conservation of angular momentum, much like the conservation of linear momentum, can be used to explain why a lot of things happen. So we have three very different scenarios here, or what seem to be different scenarios, that are all actually related to the conservation of angular momentum. The first is the fact that when an ice skater wants to spin faster, she pulls her arms in closer to herself. The second is a diver will fold up his body to increase his spin, or his rotation. The last, my favorite, a collapsing star will increase its rotational speed until it becomes a pulsar, rotating super rapidly. They spin so fast, you guys, and it's because of the conservation of angular momentum. Because the deal is, if the net torque acting on a system equals 0, so if you don't have any outside forces creating torque, then the initial and final angular momentum are equal. That is the same as saying that in the absence of a net torque, momentum, angular momentum, will be conserved. I just misspelled momentum. That's fine. Things I don't care about. So consider a student sitting on a rotating stool with a weight in each hand, as in example 11.9. If the student is initially rotating with his weighted arms extended and he pulls his arms in, the student's rotational speed will increase. But let's think about why that's true. Pulling the weights inward does what to its moment of inertia? Well, moment of inertia is larger the further from this axis of rotation the weights are. I'm doing an awkward thing where I gesture and you guys aren't here. The further the mass is from the axis of rotation, the greater the moment of inertia. So pulling that mass in towards the center is actually going to decrease the moment of inertia. And if you look at this relationship, L equals I omega, if L isn't changing because there's no net torque, then if I is decreasing, omega must be increasing. This is actually true of planets as they orbit around stars. So Kepler's second law of planetary motion states that a planet will sweep out equal areas in its orbit in equal times, as shown in the picture below. Because most things don't actually orbit circularly, they orbit elliptically. Not as elliptically as in this picture. This is, for demonstration purposes. For the shaded areas in the diagram to be equal, the planet must be moving much faster when it is closer to the sun. So it must be moving much faster here than it's moving here. This is a direct conservation of the law, a direct consequence of the law of conservation. Now I can't spell any words. Angular momentum. While your book doesn't state it as such, the law of conservation of momentum is a really big deal. It's one of the only few of conservation laws that governs the entire universe. And we've actually learned about almost all of the conservation laws that govern the entire universe. We have like one more to talk about. But things like the conservation of energy, conservation of linear momentum, conservation of angular momentum are a really, really big deal. And in some ways, the conservation of angular and linear momentum are actually a bigger deal than the conservation of energy, because it's so hard for us sometimes to talk about the conservation of energy when we have energy being quote-unquote lost to things like heat, light, sound. It's not being lost. We're not losing energy. It is still conserved. Really hard to write an equation that explains how much heat you lost during a collision. But you're never going to lose momentum if you don't have external torques or forces. Alright, let's work an example problem using this. When the planet is at point B in the picture above, it is moving with a speed of 5 times 10 to the 4th meters per second, and it is 1 times 10 to the 15th meters from the sun. When the planet is at point A, it is 2.2 meters from the sun. What is the planet's speed at point A? Treat the planet as a point mass. What did I just do with that picture? It might be nice to have the picture as we're working this. Okay. So somewhat confusingly, I guess it's because of the way the picture is set up. So we're saying that the angular momentum at point B must be equal to the angular momentum at point A. Alright, super. Since we're treating it as a point mass, the angular momentum of a point mass is mvr. So then we just need to figure out what all of these numbers they give us are. They give us velocity at point B, which is 5 times 10 to the 4th meters per second, and radius at point B, which is 1 times 10 to the 15th meters. Then they give us radius at point A, which is 2.2 times 10 to the 15th meters. And we're looking for VA. All right. MBVBRB equals, although I shouldn't have put a B on the M because it's the same planet. The mass isn't changing. So is MVA RA. So notice that the masses go away. It's the same planet, mass isn't changing, we don't care. So we have 5 times 10 to the 4th times 1 times 10 to the 15th equals 2.2 times 10 to the 15th VA. Now you can plug all of this into the calculator, or you can do what I do and realize that these 10 to the 15ths are just going to drop off. So you're actually just going to end up dividing 5 times 10 to the 4th by 2.2. And you get that VA is, what did I just do with my answer, is 2.7, 2.27, or 2.3, times 10 to the 4th meters per second. And that agrees with what we said back on this page. We said that it had to be moving faster at B than it was at A, significantly faster, because of the conservation of angular momentum. So this also explains a bunch of other natural phenomena. Oh my god, you guys, I super did the thing where I ran my 15-minute timer ran out and I didn't realize it and I kept talking and nothing was filming and it's super embarrassing. So looking at number 8, it's just talking about using this idea of the fact that conservation of angular momentum means that as something gets smaller, if it's spinning and it gets smaller, it's going to start spinning faster, to explain how storms work. So as air is collapsing inward, because you have this low pressure area that causes air to collapse inward, in a tornado or a hurricane, that's tornado, I super can't spell, don't question it. In a tornado or a hurricane, the conservation of angular momentum means that as you're getting the mass closer to the center, your moment of inertia is decreasing, so your angular speed is super increasing to like over 100 miles per hour. In the same way that a person on a rotating stool speeds up when they pull in their arms. This is the same reason that things like pulsars spin as fast as they do, because like the sun is spinning, it's not spinning super fast, but it's spinning, and when stars start to collapse in on themselves, they maintain that angular momentum, and all of that angular momentum gets crushed down into something the size of a neutron star, which if you took my astronomy mini-mester, you would know is quite small, and it has all of that angular momentum in a really small space, which means it is spinning super duper fast. Conservation of angular momentum actually also means something really interesting in terms of global warming. If the polar ice caps completely melt, it's going to change the rotational speed of the Earth. It's actually going to cause the rotational speed of the Earth to decrease, because as the mass moves outward, that's going to cause the rotational of the Earth, the rotational inertia of the Earth is going to increase, which means that omega is going to have to decrease. The book actually works out the math for this. It makes some assumptions, but it works out the math, and I think it's really cool. So if you want to look at that in the book, go ahead. Consider conceptual checkpoint 11.4. Let's say her moment of inertia is decreased by a factor of 2 when she pulls in her arms. I don't know what conceptual checkpoint 11.4 says. Let's assume it's talking about an ice skater who has her arms out and then pulls them in. So her moment of inertia goes down by a factor of 2. As a result, her rotational speed will do what? Well, rotational speed is related to rotational inertia by conservation of momentum. So if rotational inertia decreases by a factor of 2, rotational speed will increase by a factor of 2, and her rotational kinetic energy will also increase, and it will increase by a factor of 2. When I was going through this earlier, I was like, that can't be right. I don't understand. It should be 4 because kinetic energy for a rotating object is Ke equals 1/2 I omega squared. And I was like, omega squared, it should increase by a factor of 4. but I decreased by a factor of 2. So the total change is an increase of 2. This is another good question. If energy is a conserved quantity, how can her rotational kinetic energy increase? Well, remember that energy is a conserved quantity if there are no outside anything doing work. There is something doing work here. She's doing work. So the fact that she did work to pull her arms in took up some of that, or it gave her additional rotational kinetic energy. Because work is just a change in energy. She did work, we got additional energy. Alright, look at this system in terms of how we're going to think about how rotational momentum and rotational kinetic energy are going to change. We have a rotating turntable. We're dropping a stationary record down onto it. The final angular momentum is going to be equal to, less than, greater than the initial angular momentum. Well, it is going to be equal to. And there are two different ways to think about this. Number 13 down below actually has you explain each of these, and I wrote them out in advance because I write slower than I talk, so just to let you know what's going on. The way I originally thought about it was, well, this didn't have any let's see if I can use words. This didn't have any I can't use words. It's also important that we're talking about the system and not either of them, because it's going to slow this one down, right? Like, that just makes sense. It's going to make the rotational speed of this one lower, but the rotational momentum of the system is going to stay the same. And the reason for that is because there's no external torque. There's no force being done by something that's not a part of the system. This record's a part of the system, the turntable is a part of the system. So if we have no external torque, we cannot have a change in angular momentum. The final rotational velocity of the system. Well, I just kind of said that one. We kind of intuitively know it's going to go down, but in terms of explaining that it's going to be less than. But to explain that in terms of variables, we're increasing the rotational inertia, the moment of inertia, and since we just said here that L was constant, then W, angular momentum, it's not W, it's omega, angular velocity, omega, must go down. And then the final rotational kinetic energy must be equal to, less than, greater than the rotational kinetic energy. And you have to think about this equation to do so. It's going to go down because, so while I increased, and kinetic energy does depend on I, it also depends on omega squared, which means that it depends more on omega than it does on I, and since omega was decreasing, overall kinetic energy is going to decrease. Alright, so this is exactly that problem, but with numbers. A wheel is rotating freely with an angular speed of 20 rads per second on a shaft whose moment of inertia is negligible. A second wheel, initially at rest, of twice the moment of inertia, twice the rotational inertia, is dropped on top of the first. What is the new angular speed of the system? Well, the angular speed of the first object is 20 rads per sec. The angular speed of the second object at the beginning is 0. And then we're looking for their final angular speed when they're together. And those are the only numbers it gives us. So it might look at first like there's no way we're going to, oh, you can't even see what I'm doing. It might look at first like there's no way we're going to be able to get a numerical answer, but we actually can. So let's look at how that's a thing. So angular momentum is conserved. Initial momentum, angular momentum must equal final angular momentum. So I1 omega 1 plus I2 omega 2 must equal I1 plus I2, because they're like, it's the equivalent of a inelastic collision, because they're like stuck together. Omega final. This whole term is 0, because that was 0. And we can plug in, they tell us that I2 is twice as much as I1, so this becomes I1 plus 2I1. So if we rewrite all of this, we get I1 omega 1 equals 1 plus 2 is 3I1 omega f. So it actually doesn't matter what the moment of inertia of those things was. And we're solving for omega f. So omega f is 1/3 of whatever omega 1 was. Omega 1 was 20, so 1/3 of 20 gives us an answer of 6.7 rads per second. Which should make sense, because we have, well, you just have to be careful, because it might be easy to be like, oh, the new one we're dropping is twice the moment of inertia, so the speed is going to decrease by 1/2. But it's twice the original, so you end up with 3 times as much as 1. I'm not sure any of those words I just said made sense, so I'm just going to move on. And they made sense in my head. All right, here's one where we're going from having basically linear speed to angular speed, but we can still solve them both in terms of angular momentum, because remember, anything can have an angular momentum with respect to some point. And we're going to treat that point as the center of the merry-go-round. So it says we have a 30-kilogram child that runs at a speed of 2 meters. They jump on the merry-go-round that has a radius of 1.5 meters and a mass of 50 kilograms. What is the rotational speed of the merry-go-round child combination, assuming the merry-go-round acts as a uniform disk? So this is our initial angular momentum, and this is our final angular momentum. And we have 2 objects. We're going to call this object C for child and this object D for disk. So the angular momentum of our child is going to be m child v child. R perpendicular, the distance, the perpendicular component of the distance, which is just the radius of the wheel, conveniently enough. Then we would have the angular momentum of the merry-go-round, which would be I disk omega disk, but it's not moving at the beginning of the problem, so that whole piece drops out. Then at the end, just like up here, they're now one system. So now we have the rotational inertia of the child plus the rotational inertia of the disk times the angular velocity of the whole combined system. I'm going to actually go over here and set up just combining those angular rotational inertias. Disk plus child. A disk is going to be 1/2 the mass of the disk, the radius of the disk squared. Then the rotational inertia of the child is now a point mass, so it's m child r child squared. The 2 radiuses are actually the same because they're both just the radius of the circle. So we have 1/2 of 50 times 1.5 squared plus 30 times 1.5 squared. So this is 56.25 plus 67.5, which gives us a total inertia, total rotational inertia of 123.75 kilogram meters squared. I think the only difference between the units for that and the units for our per second or I'm doubting myself a little there. Again. I don't know why I doubt myself, because I was right. So now we can just go back over here. We have to plug in these things. 30 kilograms. The child was running at 2 meters per second. The perpendicular portion of the distance is 1.5 equals 123.75 omega f. This multiplies out to 90 equals 123.75 omega f, which gives you that omega f, the final angular velocity, is 0.73 rads per second.